morning. I want to thank the organisers for giving us a chance to speak today about global biosecurity. We are a non-profit, and our mission is to achieve breakthroughs in humanity's capability to prevent, mitigate, and suppress pandemics. And we primarily are working on sort of aerosol transmitted pathogens in that respect. And we have a very particular way that we go about doing that, and it's sort of the clue is in our name. And it's about providing actionable roadmaps to give people like really clear guidance about how they use their influence, spend their money to do things that they have a compelling reason to believe will make a big difference if they do those things. And this isn't our first project on far-UVC. It's our first project on far-UVC, but it's not our first project. We have a program on what we call pandemic-proof PPE, or masks, that's further along. And because we managed to come up with a clear and actionable roadmap that was based on compelling evidence, we have managed to shape and influence over $200 million of government expenditure towards having better PPE that's going to be more protective for the next pandemic, and there's still more that we intend to do in that space to make it happen. But having that actionable roadmap, the clear plan that's based on compelling evidence and science that you can explain to people why you do this thing, or if you give me this money to do this research and it's going to make the difference, that's the thing that can mobilize that kind of action. So I am in the process of trying to come up with that actionable roadmap for far-UVC, and I'm going to maybe slightly disappoint you that I'm not going to tell you what that roadmap is today, because I don't know what it is yet. But what I do think I've figured out is not the answer, but I do think I've figured out the question. And if we think about all the things that we talked about at this conference, advances in emitter technology, photobiological safety, ozone, air chemistry, all the different things that these different threads that tie together on this technology. I think there's one thing that kind of goes through all of them, and it is, how much far-UVC are you talking about using to achieve a meaningful effect in the world? And I want to kind of submit to you that all the challenges that are related to far-UVC are all related to how much you're planning to use. So I want to, these are just intended to be kind of order of magnitude points. But all of these things, the cost of and feasibility of installations, skin and eye safety, ozone secondary chemistry, the regulatory and standard environment, other things that we haven't talked about. There's some really good work ongoing there's an IUVA task force on material degradation to get really good data to make sure that we're not turning too many polymers yellow or anything like that. But the point is that I tend to anchor that, assuming that we're trying to do something in the order of this. So that's, if you take the Leeds chamber experiment, about 2.5 microwatts per centimeter squared. If we think about dosing guidelines for upper room UV and the average fluence rates that we talk about using in those contexts, that's more in the kind of several microwatts per centimeter squared. So I was definitely spending most of my time thinking about how do we solve all of these challenges to enable us to do this. But I want to submit to you that there is a different potential path based on at least some of the efficacy data that we have seen, which is that if we use about 10 times less than this, then a lot of these problems become way simpler. And if we think about just the Leeds chamber as an example of 185 equivalent air changes per hour against Staff Warriors using 2.5 microwatts per centimeter squared. My suggestion to you would be, if you want to change the world tomorrow, to use 20 times less power and still get 9 equivalent air changes per hour. And that will make a huge difference to the world if you do that. And we've got a lot fewer challenges that we need to solve. Okay, so do we believe that this world is achievable? So let's talk a little bit about inactivation rate constants. So when thinking about how to scale up things that we study in the lab into the real world, trying to measure that dose response and then trying to model that is key. I don't want to go into the derivation of these equations. It's really naive dimensional analysis with some health warnings that I'm about to give. But this is how you kind of translate a dose response curve into the kind of figure of merit that we're interested in. And then you can, this is the figure of merit in ASHRAE 241 controlling infectious aerosol. It's the kind of clean equivalent to clean airflow. Using an equation for fluency, actually I'm not going to go into the derivation, you can ask me about it later. But this is a way of translating these inactivation rate constants into figures of merit that we actually care about, right? Health warning time. You could do this for upper room UV if you so chose, but we know that that is problematic. Chamber studies of upper room UV have demonstrated the vital importance of air mixing to observe EACH. So here's some effects of adding ceiling fans in various large chamber experiments. I haven't got the slide here today for the sake of time, but there's also profound effects on ventilation design, where the inlets and outlets are in the room. Are you using forced air heating? Are you using radiators? All these things matter to generate an effective dose distribution that is sort of, I guess almost like closer to the average, where a greater amount of pathogen is getting closer to the average of the dose in the room. So I think that means that this sort of one zone model, as it were, is likely an overestimate of disinfection efficacy unless the room is well mixed. So here's just an example of a comparison of model studies from a Duncan Rim's group at Penn State, showing the estimated pathogen concentration using some fairly simple models compared to a full kind of computational fluid dynamics model of the room. And what you see is that in this particular space, it was a simulated classroom. At 5 air changes per hour, the kind of mixing in the room that was generated by that amount of airflow meant that the two models, this kind of simple one-zone model and the CFD model, kind of agreed. But at lower ventilation rates, lower mixing in the room, there was less. Now, this is for less agreement. So this is for upper room UV. And the spatial distribution of fluence rate is obviously much more extreme than it is when we're talking about whole room illumination. But I think there probably should be a sort of directionally similar effect. So I think this is very important to bear in mind when we try and scale up expectations of what we see in real-world spaces based on dose response curves that we derive from chamber experiments. With all those health warnings in mind, I'm nevertheless going to apply this equation to show you what it would tell you based on some of the data that we have. So here are inactivation rate constants from 4 studies from the Columbia group. And the thing that I want to draw your attention to is taking observations, a number of observations at relatively low doses to really understand what's going on in the first log or two of inactivation, which basically for aerosol purposes is just by far the most important. Like everything is dominated by what happens in those how quickly you get those first couple of logs of inactivation. And you get these pretty high inactivation rate constants, and then applying that one zone model, the required fluence rate to achieve 10 EACH is really small. If you cash it out in terms of equivalent clean airflow, and you think about a hypothetical device that has 100 milliwatts of output, and the average photon path length, the distance that the photon travels, is 2.5 meters, you get very large amounts of equivalent clean airflow compared to other technologies. So this, to me, is the reason to believe that you could make like a very big difference with a relatively small amount of far-UVC. But I think there's also reasonable grounds for skepticism because inactivation rate constants are so inconsistent across studies. So this is every study that we can find on inactivation in MS2. The red lines are, the red triangles are inactivation rate constants in liquid, which has a very standardized methodology that's built up over a number of years in order to get consistent results. And then the blue ones are aerosol. So these 4 here are the great constants from the study that Alvin Lai presented earlier at the conference. And these two sets for 254, the MS2 bacteriophage, are from studies from about 20 years ago. These two here are not actually really inactivation constants from a dose response study. This is my own estimate of what you get out if you apply the one-zone model to an estimate of the fluence rate in the study from the EPA that was presented yesterday. So and this is not just an MS2 bacteriophage problem, it's not just a 222 problem, this is a problem. And I just think we cannot be confident that we know how to create representative aerosol inactivation in the lab. There's reason to think that the media might be more important for far-UVC than it is for others, but this is very much not just a far-UVC challenge, this is an aerosol challenge. So I kind of think that this question, trying to figure out like how much far-UVC do we need to use to achieve a meaningful result, is a critical fork in the roadmap. And I'm not saying that because I think these problems are insurmountable. I have ideas about how to solve all of them. But I'm saying that if you don't need to, then you're much closer to being on the way to making a massive difference very quickly. So, how do we figure out which world we're living in? There's a whole bunch of different evidence that we could use to get a better picture here. And many of these different types of studies have been presented at this conference. We've had a number of chamber studies where you're studying surrogates in the lab, animal-to-animal transmission, we have a poster on that. We've got a poster on this, the Columbia Dental Clinic. And there's other things that we've heard about a proposal for a trial of human infections in representative spaces in schools in Bangladesh. Human to animal has been really important in the history of upper room UV. You can in principle do challenge trials. You can measure surrogates of human infections. There are many options for studying how well does this work using how much dose. And I don't think any one of these studies is intrinsically better than any other. And you need a combination of these things to develop the full picture, because even if you demonstrate the thing that we ultimately care about, which is infection prevention in the real world, if you don't have the modeling, then you don't know, well, what happens when I put that same amount of UV or that same device in a different space, looking at a different pathogen. So I think the answer has to be in some combination of these things where we get more consistent answers because we have an understanding of the kind of causation of what's going on. But my question, I think if we can answer this question, then we'll be on a long way to sort of cutting the Gordian knot of all of the threads that tie together when trying to understand the potential of this technology. If we can figure out what to do next to get a better sense of the answer to this, then I think that is the answer to a clear and actionable plan that will motivate people to deploy resources and use their influence to advance this technology. So I'm doing my best to try and figure out what the answer is to that question so that we can present it to people who will be able to help make it happen. But I need your help. All the work that's gone into this in the last year has been supported by so many people in this community, in conversations, debates, all kinds of different interactions that we have had. Some of you have reviewed material that we have written and provided really helpful feedback. This is just a link to a comment form because I want to hear what you think about what I said today. Please email me, I would love to talk to you. And yeah, I'm really looking forward to getting some questions. So thank you very much.